Most people like to believe something is or is not true. Great scientists tolerate ambiguity very well. They believe the theory enough to go ahead, they doubt it enough to notice the errors and faults so they can step forward and create the new replacement theory. If you believe too much you'll never notice the flaws, if you doubt too much you won't get started. It requires a lovely balance. Richard Hamming. Richard Hamming emphasized that to do great work, you need to work on important problems, not just any interesting ones. He stressed the significance of having a vision and the courage to pursue it, even when facing difficulties. Hamming believed that while talent is helpful, consistent hard work and a willingness to learn and adapt are crucial for making significant contributions. He also highlighted the importance of communicating your work effectively and integrating with the broader scientific community, rather than working in isolation. Richard Wesley Hamming was born on February 11, 1915, in Chicago, Illinois, to Richard J. Hamming, a credit manager, and Mabel G. Redfield. His father was of Dutch descent, and his mother was a Mayflower descendant. Growing up in Chicago, he attended Crane Technical High School and Crane Junior College. Initially, Hamming aspired to study engineering, but the Great Depression limited financial resources, and the only scholarship he received was from the University of Chicago, which lacked an engineering department. Consequently, he pursued science, majoring in mathematics, and earned his Bachelor of Science degree in 1937. Looking back, Hamming considered this a fortunate turn, remarking that as an engineer, he might have been going down manholes instead of engaging in the excitement of frontier research. He continued his education, obtaining a Master of Arts degree in mathematics from the University of Nebraska in 1939. Richard Hamming's initial foray into significant academic work culminated in his doctoral dissertation, Some Problems in the Boundary Value Theory of Linear Differential Equations, a substantial piece of research he undertook at the University of Illinois at Urbana-Champaign. Completed in 1942, this work was conducted under the guidance of his doctoral advisor, Waldemar Trzeciński, a noted mathematician specializing in analysis and differential equations. In his research, Hamming built upon the existing work of his advisor, Trzeciński. Trzeciński's own research often involved intricate analysis of linear differential equations and their properties. Hamming specifically concentrated on the concept of the Green's function, a powerful tool in the study of non-homogeneous linear differential equations. The Green's function essentially provides a way to construct the solution to a non-homogeneous equation based on the solutions of the corresponding homogeneous equation and the non-homogeneous term. It acts as a kind of influence function, showing how a point source represented by the non-homogeneous term affects the solution at other points in the domain. Joining the mathematical research department in 1946, he found himself in an environment teeming with brilliant minds, including Claude Shannon and John Tukey, with whom he would collaborate and share ideas. This period was characterized by his deep engagement with the computational challenges of the time, particularly with the early relay-based computers like the Bell Model V. Hamming's work during these years was multifaceted. While the error-correcting codes became his most famous contribution, he was also involved in a variety of other mathematical and computational problems relevant to Bell Labs' interests in telecommunications. These included work on numerical methods, the stability of complex communication systems, and various mathematical computations for engineering problems such as traveling wave tubes and the equalization of television lines. A pivotal aspect of this era was Hamming's direct interaction with the limitations of the early computing technology. He experienced firsthand the frustration of unreliable systems, particularly the punched card readers used for input on the Bell Model V, which frequently produced errors that would halt computations. It was this practical problem, the need for reliable computation, that directly motivated his investigation into automatic error detection and correction. He spent considerable time working on the Model V, grappling with its intricacies and the challenges of programming it effectively. His experiences during this time, trying to run long computations over weekends only to find they had failed due to single-bit errors, were crucial in shaping his thinking towards the development of his error-correcting codes. Richard Hamming's 1950 paper, titled Error Detecting and Error Correcting Codes, published in the Bell System Technical Journal, stands as a monumental work that fundamentally shaped the landscape of digital communication and data storage. Born out of his direct experiences with the unreliability of early computing systems at Bell Labs, particularly the frustrating prevalence of errors in the electromechanical relay-based computers, this paper presented a revolutionary approach to ensuring the integrity of digital information. Prior to Hamming's work, the prevailing method for dealing with errors in computation and data transmission was primarily detection. Systems might employ parity checks, where an extra bit is added to a sequence of bits to make the total number of ones either even or odd. If a single bit error occurred during transmission or storage, the parity would be incorrect, signaling that an error had happened. However, parity checks could only detect the presence of an error. They offered no mechanism to identify the location of the error and thus no way to correct it automatically. When an error was detected, the only recourse was usually to retransmit the data or rerun the computation, which was inefficient and time-consuming. Hamming recognized the limitations of this approach and sought a more robust solution. His key insight was that by strategically adding redundant bits to the original data, it would be possible not only to detect errors but also to pinpoint their exact location, thereby enabling automatic correction. This idea was groundbreaking because it moved beyond simply acknowledging the presence of corruption to actively restoring the original, correct information. In his paper, Hamming meticulously laid out the theoretical framework for constructing such error-correcting codes. He introduced the concept of Hamming distance, which is defined as the number of positions at which the corresponding symbols are different between two strings of the same length. For binary code sequences of zeros and ones, the Hamming distance is simply the number of bits that differ. Hamming astutely realized that the error-detecting and error-correcting capabilities of a code are directly related to the minimum Hamming distance between any two valid code words, the encoded data sequences. Specifically, he demonstrated that a code with a minimum Hamming distance of d can detect up to d1 errors. Furthermore, if the minimum Hamming distance is 2t plus 1, the code can correct up to t errors. This fundamental relationship provided a mathematical basis for designing codes with specific error handling capabilities. The paper then went on to describe the construction of a family of linear block codes, now known as Hamming codes. These codes are characterized by their efficiency. For a given number of information bits, they add the minimum number of redundant bits required to achieve single-bit error correction. Hamming provided a systematic way to determine the number and placement of these redundant parity bits. These parity bits are calculated based on specific subsets of the information bits, such that if a single bit error occurs in either an information bit or a parity bit, the pattern of incorrect parity checks will uniquely identify the location of the error. 1962, Publication of Numerical Methods for Scientists and Engineers. This became a widely used textbook, reflecting his deep understanding of numerical computation and its practical applications. A second edition followed in 1973. 1968, received the ACM Turing Award for his work on error-correcting codes and his contributions to numerical analysis and the design of automatic programming systems. This award itself signifies a major recognition of his lasting impact. 1971, publication of Introduction to Applied Numerical Analysis, another significant textbook in the field. Richard Wesley Hamming passed away on January 7, 1998, in Monterey, California, at the age of 82. His death marked the end of a remarkable life and a highly influential career that spanned mathematics, computer science, and engineering. While the immediate cause of his death was not widely publicized, it occurred after he had retired from the Naval Postgraduate School, where he had been a distinguished adjunct professor since 1976. Even in retirement, Hamming remained intellectually active, continuing to lecture and share his insights on the art of doing science and engineering. 1977, publication of Digital Filters. This book was a comprehensive treatment of the subject, reflecting his extensive work in this area and introducing the widely used Hamming window for signal processing. Second and third editions followed in 1983 and 1989. 1980, publication of Coding and Information Theory, formalizing and expanding on the principles he laid out in his 1950 paper and related concepts. A second edition was published in 1986. Also published his influential essay The Unreasonable Effectiveness of Mathematics in the American Mathematical Monthly. 1985, publication of Methods of Mathematics Applied to Calculus, Probability, and Statistics, showcasing his broad mathematical expertise and its applicability across different scientific domains. 1986, gave the influential lecture You and Your Research, which, while not a traditional publication in a journal, has had a significant impact on how researchers think about their work and careers. It was later transcribed and widely circulated. 1991, publication of The Art of Probability for Scientists and Engineers, demonstrating his ability to explain complex mathematical concepts in an accessible way for a scientific audience. 1997, publication of The Art of Doing Science and Engineering, Learning to Learn. This book, based on his popular lectures at the Naval Postgraduate School, encapsulates his wisdom and insights on how to conduct impactful research and foster innovation. 1998, posthumous publication of Mathematics on a Distant Planet in the American Mathematical Monthly, reflecting on the fundamental nature of mathematics. When you are famous, it is hard to work on small problems. This is what did Shannon in. After information theory, what do you do for an encore? The great scientists often make this error. They fail to continue to plant the little acorns from which the mighty oak trees grow. They try to get the big thing right off. And that isn't the way things go. So that is another reason why you find that when you get early recognition it seems to sterilize you. Richard Hamming. Richard Hamming received numerous prestigious awards throughout his career, recognizing his profound contributions to computer science, information theory, and numerical methods. 1968, ACM Turing Award, awarded by the Association for Computing Machinery for his work on numerical methods, automatic coding systems, and error detecting and error correcting codes. This is often considered the Nobel Prize of Computing. 1979, IEEE Emanuel R. Pior Award, awarded by the Institute of Electrical and Electronics Engineers for introduction of error correcting codes, pioneering work in operating systems and programming languages, and the advancement of numerical computation. 1980, member of the National Academy of Engineering. Election to the NA is among the highest professional distinctions accorded to an engineer. 1981, Harold Pender Award, awarded by the University of Pennsylvania for outstanding achievements in engineering. 1988, IEEE Richard W. Hamming Medal, established by the IEEE in his honor, and he was the first recipient. This medal is awarded annually for exceptional contributions to information sciences, systems, and technology. 1994, Fellow of the Association for Computing Machinery, recognition as a distinguished member for significant accomplishments in computing. 1996, Eduard Rhein Award for Achievement in Technology, a prestigious German award recognizing outstanding achievements in technology. Thanks for reading No Mic Podcast Scribed by Facelesslingjutsu. Subscribe for free to receive new posts and support my work.